Perfect. All right. So let's start with the first reaction. So it's the hydrohalogenation reaction. I'm going to kind of go through these pretty quickly. So again, remember, nucleophile attacks that electrophilic proton, forms a carbocation on the more substitute position, which is the tertiary position in this situation. And then that bromide is going to come in and attack that tertiary position. So essentially, I'm going to expect a structure that looks like this. Did I generate a chiral center? Yes, I did. I have a methyl, an ethyl, and a propyl group. So I have to consider both major stereoisomers. So either that bromide attacking on the top base of that unhybridized p orbital, or that bromide attacking on the back base of that unhybridized p orbital. Okay, and that would be the two major stereoisomers for A. For B, you can imagine we have this kind of cyclic, halonium bridge of this bromide right here, and we have water attacking at the more substitute position. But remember, if that bromide bridge were on, wedges, that means water must attack anti, so on a dash. And again, if that bromide bridge was on a dash, then that water would have to attack on the front face, wedge, essentially. So your two major stereoisomers for these, oops, that comes off the same thing, would be, let's say, if the bromine bridge was on a wedge to begin with, water must have came in on the back face. And then likewise, we can also say if bromide bridge was already on a dash, that water must have came up on the front face, forcing that methyl group back. Okay, and those are our main stereoisomers for B. Okay, so for C, we have our alkyne double dehydrohalogenation reaction. Essentially, we're going to form an internal alkyne. So that internal alkyne is going to form in between carbons 1, 2, 3, carbons 4 and 5. So I'm going to draw a 1, 2, 3, 4, 5. 1, 2, 3. Oh, it's between 4 and 5. My bad. 1, 2, 3, 4, 5, 6. So that's what it should look like. I'll number that for you guys. 1, 2, 3, 4, 5, 6. Okay, that's the structure there. And then sodium, pure sodium metal, and ammonia is going to form that alkyne into a E-alkene. So it's 1, 2, 3, 4, 5, 6. And remember, it's between 4 and 5. So 1, 2, 3, 4, 5. So that would be the product of step 2. All right. So for D, we have the, it looks like the hydroboration oxidation reaction for alkynes. Okay, so we're going to form that, remember, enol tautomer on the less substitute position. So this is a 1, 2, 3, substituent on that ring. So 1, 2, 3. Okay, and on that third position, we're going to form that enol. Okay, so I'll put this H here. And we said that that enol is going to readily tautomerize into the keto form. So the keto form is going to be 1, 2, 3, and an aldehyde. Okay. That's right. For F, we're going to have the reduction of alkynes, so catalytic reduction. And remember, it's syn addition, so you have to remember that you have to draw one of these stereoisomers, and I'll explain why one. And if you were to draw the second one, maybe you would understand why you only needed one. There's a plane of sigma symmetry, so if you were to pancake flip that over, it would be the exact same structure. So we can just say that there's one product that's meso. Okay, syn addition. For G, remember we're going to do these hydrohalogenation reactions for alkynes. So the result is, a carbocation on the more substitute position, and then that chloride coming and attacking there. So it'd be a 1, 2, 3, 4, 5 carbon chain. 1, 2, 3, 4, 5 carbon chain. And then between 1 and 2, we would have formed this intermediate right there. And then chloride would have attacked. So we would have this as a result of step 1. And then step 2, we're going to form a carbocation there again. So step 2, we would form something like chloride and bromide. Okay, but in this situation, it looks like we generated a chiral center. So then we would have to consider the major stereoisomers of that. So it would be a wedge chlorine dash bromide, and then wedge bromine dash chlorine. Okay, so that's that guy. And then for H, we're going to have, looks like H2 and Lindlar. So H2 and Lindlar is going to reduce alkynes into Z-alkenes, but not touch this alkene, okay? And that should make sense in a second. 1, 2, 3, 4, 5, 6, 7. So it's a 1, 2, 3, 4, 5, 6, 7, okay? And specifically, that alkyne was between 1, 2, 3, 4, 5, and 6. So 1, 2, 3, 4, 5, and 6. So I actually need to redraw that. 1, 2, 3, 4, 5, 6. There we go. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. Sorry. Z. I keep doing that. I did the same issue above. Okay, so let me explain this again. So H2 in Lindlar is going to reduce this alkyne into a Z alkene. That's why I had to draw this methyl group down. I keep making that mistake. It has to be down. Okay, and it's not going to touch this original alkene because H2 in Lindlar is a weaker version. So remember, H2 platinum, palladium, nickel is the strong stuff. So that's going to always make alkanes, okay, all the way down. But H2 in Lindlar or sodium and ammonia, which we saw up here, those are the weaker versions, okay? So we still have pi bonds that result from these. They don't completely take away all the unsaturation points, okay? And that was just kind of a quick overview of like all of your chapter 6 and 7 reactions, or most of them. Any questions on these warm-up questions today? Any of them? Okay. Awesome. So let's move on to the synthesis for the day. So we're just going to literally spend almost all of our time on these synthesis problems. I think that's kind of your biggest concern for this test anyway at this point. So yeah, so basically there is no one correct way typically to do these. Honestly, more often than not, there are multiple ways to do it. So if you guys have another valid route that you guys want to share or, you know, type in and say, I can also check those to make sure that they're right. Okay, so what do we want to do here? So for 9A, it looks like, you know, we're starting from a 1, 2, 3 carbon, you know, substituent on that benzene ring. And then, you know, that 3 carbon substituent turns into a, you know, a 4, you know, it becomes 4 carbon chain and then this whole cyclic structure on there. So we only know one reaction at this point that makes bigger molecules or, you know, extends the carbon chain. And that is the acetylide addition reaction, okay? So we know at some point in 9A, we have to do that acetylide reaction where we form that, you know, terminal alkyne acetylide anion, and then we attack some sort of haloalkane to extend the carbon chain. So I know I have to do that, right? That's the most obvious thing we have to do here. So let's get to that point. Let's get to this, you know, acetylide reaction. So how should I do that? Well, first I want to make an alkyne from this alkene. So if you have no idea where to start, remember we can form alkynes this way. We can do Br2 and maybe some like inert solvent. Let's just do like DCM. And the resulting structure is going to be something that looks like this. And you don't have to draw, you know, stereochemistry in these synthesis problems because, you know, they're going to be either taken away or formed in subsequent steps. So you don't have to worry about stereochem for now. So that's the result of step 1. Step 2, I can do that double dehydrohalogenation reaction. So that's going to make my alkyne. So that's going to be like, you know, maybe Na, NH2, NH3. And let me do 3 equivalents of that. Okay. And then that would result in maybe a structure that looks like this. 1, 2, 3 carbons. So 1, 2, 3 carbons. Okay, so we have that acetylide anion. Hope you guys can see that. And then if I wanted to treat that maybe in step 2 with, let's just say, this whole carbon fragment. Remember, we need to form this. It looks like, where's 1, 2, 3 carbons? So it's the 4th carbon, this 4th carbon and the ring. So this, you know, 4th carbon and the ring. That's 4 right there, 4th carbon and the ring. Okay, so then those reacting would form, you know, this structure. Yes, sorry, thank you. So we have this structure. So here's 4, now in the ring. So okay, so we're there. So we're pretty close, and we like that. And it looks like we need to get to this, I guess, bromide. This is the abyssal bromide structure. So, you know, I don't want to add 1 equivalent of bromide in here because then I would be left with a pi bond still. I basically want to maybe do 1 reduction step, maybe get that to an alkene, and then do bromination. Does that kind of make sense? If I were to just do Br2 from this step, you'd be left with a pi bond here still, okay, a pi bond in this material, and we don't want that. We want a reducing step maybe to this alkene and then add the bromine. So let's do that reduction step. Maybe like pure sodium and NH3, so pure sodium and ammonia, to get a structure that looks like this, and I can move that back up. So it's a 1, 2, 3, 4, so 1, 2, 3, 4. Okay, between 3 and 4. 1, 2, 3, actually, sorry, 1, 2, 3, here. Okay, and then you're one step away from that, and it's just Br2 and then DCM. Okay, can I combine the bottom 2 steps in one chemical step? Yes, you can. I purposely would have run a 1 there. I forgot to write the 2 there. You can put that together, these 2 steps together, okay? I like to show them separately just because, you know, it shows each consecutive step, but yeah, you can totally put those together, 1 and 2. Does anybody have any other, you know, questions on this one or other routes that they did to get that answer? Or has any other questions in general? Okay, so the biggest hint for you guys right now, and I would write this down or whatever, is if you see a carbon chain get bigger, like clearly went from, you know, 3 carbons here to this, you know, longer carbon chain here, you had to have done acetylide addition somehow. So your best hint is to somehow use that starting material, get to the acetylide, and then when you get to that acetylide, you can just kind of see the future once you get there, I guess. And I got a couple questions going on. Let's see. Can you explain the number of equivalents, like why 3 equivalents? Yeah, sure. So essentially, what the first equivalent was going to do is, let's just draw these hydrogens in here to make this make sense. So what the first hydrogen does, for the first equivalent, it's going to take off that H, donate that into the ring, and kick off the bromine. Okay, so that forms a alkene. Then the second equivalent is going to take this H off, donate into the ring, and kick that bromide off. So that's going to form an alkyne. Okay. But since it's terminal, there's a terminal third proton here, okay? So what that third equivalent does is it takes that last proton off of here and forms that acetylide anion. So that's why it's 3 equivalents. Okay, good, yep. Anybody have any more things that they want clarified on A? I know this is a tough subject, or topic, I guess. All right, cool. So 9B. So clearly, I have a longer carbon chain. Okay, and it's nice that I start with this kind of ethylene structure. So ethylene is going to be a 2-carbon alkyne. And it looks like I have 2 protons to work with. And it looks like where these main functional groups are, like this area, there were things added to the left, like maybe this methyl group, and things added to the right, maybe this, you know, longer alkyl chain. So I could actually do 2 rounds of acetylide addition. Let's just do that to start with and maybe get some insights there. So maybe my first step would be to do, you know, NaNH2 and ammonia. And this is 1 equivalent, okay? And that is going to form, and then step 2 of that is going to be whatever, you know, alkyl halide that you want to start with. Let's just say I want to add the left fragment first. So that would be a CH3Br fragment. So maybe I'm going to do CH3Br. Okay, so that's a 1 carbon. See, I'm adding 1 carbon. That's my 1 carbon. Okay, so then the resulting structure would be, you know, this. So I added that 1 carbon right there. Okay, let me do another round and maybe add this whole right side. Okay, so 1 would be NaNH2 dissolved in ammonia, which is 1 equivalent. Okay, and then, you know, I want to add this whole carbon chain. So it looks like it's a 1, 2, 3 carbon chain with 2 methyls coming off of carbon 2. So 1, 2, 3 carbon chain with 2 methyls coming off of that carbon 2. Okay. So then that would lead to the structure that looks like this. Okay, so 1, I guess, 1, 2, 3, and 2, 2. Okay, so now we're there. So we're pretty close. And it looks like the next thing, like the last step, is trying to somehow get to this, I guess, adjacent alcohol structure, or this syn diol. Okay, so this is what I was talking about a couple of times in office hours, where if I want to form a syn diol, I have to go to that Z alkene. So how do I go to that Z alkene? H2 in the middle. So it'd be a 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. And between 1, 2, 3, 1, 2, 3, we have a Z alkene. So let me draw that again in the Z form. Sorry, 1, 2, 3, 4, 5, 6. Okay, so it should look like that. Okay, make sure it's Z. Okay, so that's the Z structure. And then we have one step away, osmium tetroxide, water, and hydrogen peroxide. And you're there. Okay. Any questions on this one? Pretty easy. So you can do multiple rounds of acetylide addition if you have, this ethylene structure. And specifically, just remember, if you're doing that syn-diol synthesis, you want to make sure you get to that Z alkene. And I think I just got a question to that. Why? Let's see, what does that say? Why do you need the Z form of the alkene? Yeah, so it's this concerted mechanism. And let me show you what that looks like. So if I were to get this paper, okay, and I were to show that this is, that structure, and I showed this mechanism of how it approaches. What happens is that pi bond, is going to go here, and that's going to swivel over. Okay, so the resulting structure is this, this, kind of intermediate. And the only way to get this mechanism is to do it through this kind of Z fashion, this Z orientation. You can tell in these arrows, they have to approach in this proximity or in this kind of geometric arrangement in order to form that syn-diol. So once this is hydrolyzed with water and regenerated with peroxide, you're going to get this, I'm just going to OH. And then the only reason why you see a dash is because they rotated back down to the E trans format. So remember, if you could rotate this up, you would see that it's hydroxyl on a wedge, which would be this structure. All that we did in the last step was go back down. So if it wasn't Z, form the two oxygens could add in an anti-form or different phases. It wasn't Z, the two oxygens could add in an anti. Yeah, so is that question more like if it was the E alkene, you couldn't do this reaction? Is that what you're trying to say? Yeah. Let me make sure that's true before I say that. Give me 1 sec to verify that. Yeah, they have to be Z. Okay, so all the reactions that I've seen only have the Z alkene going in there. Okay, I hope that gives you some clues. Yeah, anybody else? All right, so let's keep moving. So here we go. It looks like we're extending the carbon chain, as you can see. Maybe, we have this methyl group already over here, and this is maybe my main alkyne. So looks like I'm adding a 2 carbon fragment to the right. So I know how to do that at this point. So it would be NaNH2. This results in NH3, 1 equivalent. Okay, and step 2 is going to be that 2 carbon fragment. Okay, so the resulting structure of that is going to be this, 1, 2 structure. All right, and which one am I on? Yeah, and the next step we want to do is see how we can get these tetrahalides on there. Okay, well that's pretty easy. This one I would just want to flood it with an excess of bromide because we know that these alkynes can do these halogenation reactions. So Br2 and DCM as the solvent, and maybe I'll do 2 full equivalents because if it's 2 equivalents, it's really 4 bromides. And there you go. And then you're there. That's it. So this one was pretty easy to see. All right. So let's look at D. So for D, it looks like we have a 1, 2, 3, 4, 5 carbon chain, our main parent chain. 1, 2, 3, 4, 5 parent chain over there. So we're not going to do acetylide addition here. But what it looks like is we have these halides and we want to go to an alcohol. So that's weird. When I see 2 halides, it's just immediately telling my brain to do dehydrohalogenation. I don't know why, it just is. So let's just try that. So the results of this step would be forming that, terminal alkyne. So 1, 2, 3, 4, 5. So it's 1, 2, 3, 4, 5. And it looks like that. Okay, so we are at that structure. Then I want to know how I can make this structure into an alcohol. Well, I don't really know how to make just an alcohol from alkynes, but I do know that I can get to the alkene. So let me just do like maybe Na, pure sodium and ammonia to get the E-alkene. So it's something like 1, 2, I guess you could say. So that's the E-alkene. And then from that E-alkene, I just need to do one more reaction to get to that. It looks like anti-Markovnikov alcohol. You can see it's on the less substituted position of that pi bond. Clearly, it's the primary position. So that I would just do hydroboration. So I would just do BH3, CHF. Step 2 would be sodium hydroxide, and I think it's peroxide if I'm correct. NaOH, yep, H2O2. And there we go. Yes, so let's see. We got some questions going on here. All right. Why would you use 3 equivalents? Could you just use 2? Okay, let me explain. Okay, fair. Let me try and explain this in like a logical way. All right. So if I know we said this in the last office hour, it's kind of confusing. Like, why do I have to remember to use 3 for terminal and then for internal it's 2? And it seems kind of redundant. What the third equivalent does is it does remove that final proton, okay? And step 2, it's like stupid. It like puts it back on. So why are we doing this? If I were to use just 2 equivalents of it, there would be slightly some amount of, end product that is acetylide anion, okay? Because if I have full stoichiometric balance, meaning complete like 3 equivalents of base for 3 equivalents of protons, every single product will look like this, okay? If it's not fully the 3 equivalents, you might have some that, are kind of like this, are kind of half deprotonated, are completely like this. So in order to get this completely isolated product, and at least in synthesis, you have to show the 3 equivalents. I kind of hope that made sense. I know that was a weird definition, a weird explanation. Okay, and okay, here we go. Could you use the hydroboration of alkynes? Okay, okay, that helps you use 2 equivalents for middle ones. Yes, that does, Farah. Always use 2 equivalents for middle ones and 3 equivalents for the terminal ones. And Zoya, okay, could we use hydroboration for the alkynes? Did you want to hydroborate from this step to your end product?
Yeah.
Okay, so you can't actually do that because remember, it doesn't just form an alcohol, it forms the enol, okay? So it's like you're removing one of the pi bonds and putting the alcohol in its place, so that would be the enol that you form, and then that goes to the keto form. Remember, that goes to the aldehyde, okay? So
Okay,
just keep
yeah.
that, keep that.
Okay, thank you.
Yep. All right, anybody else has anything there though? These are great questions, everybody. Yeah. All right, so let's just move to the next page, so we're halfway done. Good. So you guys see it. It's not like so terrible, at least at this point, because you guys only are limited to actions, but you guys can definitely see how it could build, in the future. So good to get this down now. All right. So for these guys, so it looks like we have this again double halogen structure, and I only know one reaction with these double halogen structures, and that's just a dehydrohalogenate. So let's just start there. It's kind of logical actually. So the first thing I would do is just deprotonate all those things. So NaNH2, NH3, and again, back to this question, Farah, why would I do, 2 versus 3 equivalents here? I would use 3 specifically because it's at the end, okay? So I hope that kind of makes sense now. And then that would form, this, I guess 1, 2, 3, 4. So it's between 3 and 4. So 1, 2, I guess 3, 4 structure. Yeah, that works. Okay, and really easy, it looks like. So again, I want to form this aldehyde structure. So I know I can form the enol at the less substituted position, which tautomerizes into the keto form at the less substituted position by using what we all just said. I think Zoya just said it. It was this diacetic isoamyl borane THF, and then step 2 would have been, that source of hydrogen. So this was a 2-stepper, really easy. So again, this was an obvious sign to, use that dehydrohalogenation condition to get there. And then once I was there, I was like, oh my God, I can just do hydroboration to get to, that aldehyde on the last substitute position. Okay. So any questions on that one? Great. So for F, so clearly telltale sign, let's do an acetylide addition reaction. Okay, we're extending the carbon chain somehow. I only know one reaction to get there. I need to prep some sort of acetylide alkyne, starting material. Okay, so I have this alkene. I don't know how to make an alkyne from this position yet. So what you can do is let's halogenate. Okay, and this is just like what we saw above in E. So if I get this structure, it's really easy to get an alkyne from there. Okay, and okay, so we can see how that would form the acetylide anion, okay, at the terminal position. But then how many carbons am I adding? So it looks like 1, 2, 3, 4. 1, 2, 3, 4. It looks like a 5 in the ring. So a 5th carbon in the ring. So that's the 5th carbon in the ring. All right. So in doing so, you would get, this structure. Let me draw it over here. Okay. So that's the alkyne in the middle. And then how do I completely get rid of that alkyne? Really easy. We're going to use that strong reducing agent. Remember, the stronger version was H2 and any of those platinum, palladium, or nickel guys. And that gets rid of all the saturation points, unsaturation points, I should say, and makes it an alkane. Okay? So a very important thing I want to point out here, and it's going to be common in exam 4 synthesis as well, is this series of steps. Okay? So know how to get from an alkene to an alkyne. Let's draw that. Alkene to alkyne is very important. Okay, so I'm going to draw that in red at the top so you guys remember this. This is going to be the most helpful piece of information you guys can know in terms of synthesis for the test. How do I get from alkene to alkyne? Okay, so we would have to halogenate first. Okay, because remember that forms that, I guess, vicinal halide, so I can call it a vicinal haloalkane, which basically just means 2 adjacent halogens on an alkane. That's all it means. Then you can dehydrohalogenate. With these, reagents right here. That's the NaNH2 guy, NH3, and you're there. Okay? So it's weird. It's kind of like alkene to almost alkane back to alkyne, but that is a very important thing I would know for your test on Friday. Okay? Anybody confused on what I'm saying by that? Alkene to kind of this haloalkane to alkyne. That's like, if you're ever stuck, just think back to that. That typically will help you guys. Anybody else? Okay, let's keep going. So for G, all right, it looks like I'm forming 2 products. Okay, so that should make my brain start thinking, what reactions do I know that actually kind of like form 2 separate products? So it could be, maybe hydroboration. It could be, oxymercuration of alkynes, any of those of alkynes. We also know ozonolysis. That's a way that we can cleave pi bonds to form these, carbonyls. So those are the 3 things I'm thinking of as my last possible step. So maybe I can write that out here. So ozonolysis, maybe question mark, maybe some alkyne reaction. I don't know. Those are 2 ways that I'm thinking of. You can write that out on the side of your paper. That's maybe my 2 last things. But more specifically, if I were to look at these 2 structures, I see that I have 1, 2, 3. Okay. And it looks like here I have 1, 2, 3 as well. So it looks like I have to do 2 rounds of acetylide addition, okay, to start with. And it may not be clear why, but it'll make sense maybe later. Okay, so NaNH2, NH3, and this time I'm only doing 1 equivalent. Okay. In step 2, I want to add this 3 carbon chain. So 1, 2, 3, bromide. Okay, so that's 1, 2, 3, bromide. And the resulting structure would be 1, 2, 3, and the bromide. Let's do it again for the other fragment or the other side. Let's do, NaNH2, NH3, in this one equivalent. Okay. And then step 2, I want to add this whole carbon chain. So it looks like 1, 2, 3, and there was 2 methyl groups on 2. So that looks like that. And then my end product is going to look like this. Okay, so we're there. So that was a way we did this. Remember, when you see ethylene like this, you can pretty much guarantee that you're going to do 2 rounds of acetylide addition because these protons are both there. Like, it's kind of a big obvious hint. So now we got this main parent structure. How do I, maybe get these 2 identical, these 2 structures from this alkyne? Well, maybe I can reduce it to the alkene and then just do ozonolysis. Like, that's kind of the most important thing for me, at least, or the most obvious thing I see. So I would just do like any of these. It doesn't matter which one you use. This would be a 1, 2, 3, 4, 5, 6, 7, 8 carbon chain. So 1, 2, 3, 4, 5, 6, 7, 8 carbon chain. And between 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. You got this alkene. Okay. And then the last step would just do to ozone and DMS, dimethyl sulfide. And you get there because it cuts and puts aldehydes. Remember? That's it. But you can kind of see, like, they're all kind of like the same theme. It's like manipulating this alkene or alkyne starting material to get to a new alkene or alkyne somewhere else, and then just doing one of your like earlier reactions, like ozonolysis or acid catalyzed hydration or syndiol synthesis, any of those. So, and you can kind of catch this theme. It's like either extending the carbon chain because that's all you can do at this point, and then manipulating at the end, or maybe forming that alkyne and then doing some other things later on. So these are kind of your common themes so far. All right, we have 2 more left. So let's do H and I. Okay, so I'll give you guys a second to think about H. So I don't want to just give you the answer right. So somebody put in the chat box the first thing they're thinking when they see this. Somebody, what do they think? What reaction? I'm gonna wait till somebody does it. Add onto the chain, perfect. Yeah, so how do I add onto the chain? That's the acetylide addition that we've been seeing over and over again. Great. So actually, Hannah, in this specific example, we're not going to use 3 equivalents, and I'll show that why now. Okay, so essentially the first step is going to be using NaNH2 dissolved in ammonia, and that's 1 equivalent. 1 equivalent because we only have 1 proton, so we only need 1, a stoichiometric quantity of this reagent to fully remove 1 mole of those protons. Then step 2, it's to, we have 1, 2 carbons here, 1, 2 carbons here, but it looks like we're adding 3, 4, this whole group. So essentially what that is, I can just draw that. Okay, so that's going to add this kind of 1, 2, 3 group, which is this 1, 2, 3 group over there. Okay, 1, 2, 3 group. And the resulting structure of that is going to be, now a structure that has the right amount of carbons in this parent chain. So that would be a structure that looks like this. Okay. So now, how do I specifically get it looks like an alcohol at this, really substituted or more stable position? Well, I don't really know how to get just an alcohol from an alkyne. So let me just go to this alkene. So I don't care which one. Let me just pick pure sodium and metal. So it's 1, 2, 3, 4 carbons. So 1, 2, 3, 4 carbons. Okay, and that's where my pi bond was. And this is really easy. This is the first reaction, one of the first reactions. This is just acid catalyzed hydration because this is the more substitute position. It adds on an alcohol, and you're done. You kind of see what I'm saying? It's either some sort of like acetylide thing going on, and then like just a regular alkene reaction at the end. That's a regular alkene reaction at the end, or a regular alkene reaction at the end, a regular alkyne reaction at the end. What is the other option to reduce alkynes? H2 and Lindlers. H2 and Lindlers was the other one. Yep. And that forms the Z alkene. Okay, that would have been the other one. That's okay. All right. Anybody have questions on that?
I have a question.
Sure.
I didn't want to type it. So based on the notes and what we learned, isn't H2 Lindler able to reduce alkynes to the cis alkene or the Z alkene, right? So,
H2 and Lindler.
because when I was doing the
Yes.
homework last night, I tried to like interchange the sodium and NH3 and the H2 Lindler, and it kept telling me that I was getting it wrong. It was also really late, so I might have been also just getting it
Yeah,
wrong
so
earlier.
there is a difference between those two. So the sodium and ammonia one and the H2 and Lindler guy are both going to make alkynes alkenes. The
Right.
difference is just E or Z. That's it.
So so
Yeah.
on the exam, when I'm trying to reduce the alkyne to the alkene, does it matter which one I use? Because you say it doesn't matter, but
It doesn't matter for most of them. The only one I think it matters for, which I said earlier, was this guy right here. Whenever, if your
okay,
last step is to form that syn diol, it has to be Z. So you had to have used H2 and Lindler before.
okay, that makes
Does that make
sense.
sense? But I think that's
Yeah,
really the only one. Everything else you can kind of just like pick either or. It doesn't matter.
right. So if I'm just trying to reduce the alkyne to the alkene, I can use either or, except for when we're doing that one mechanism.
Exactly. Correct. That works.
Okay,
Yep.
thank you.
Did everybody else get that? That was actually a really good question. I hope that makes sense. Basically, what she was saying was essentially, we just, when we're taking these alkynes and we're making them alkenes, you can use two options, either the sodium and ammonia one or the H2 and Lindler guy. It typically doesn't matter for our synthesis problems, except for that one osmium tetroxide guy, where it forms that syn diol, where you would have to use H2 and Lindler in that case, for reasons we talked about. Farah, does the oxymercuration mechanism work in place of the acid catalyzed hydration? Okay, so Farah, yeah, remember, oxymercuration could also, it does typically the same thing as acid catalyzed hydration. However, this mechanism doesn't go through, the oxymercuration mechanism doesn't go through a carbocation intermediate. So be careful in synthesis because you might need to rearrange in a synthesis problem. You know, you might need to like move that alcohol in a position, you know, to a more stable position. And if you chose the HGOAC reagent, it wouldn't be possible because there's no carbocation. So typically you can interchange those, yes, but be careful because sometimes there might be a rearrangement that you need. Okay. Okay, so does equivalency depend on the amount of protons attached? Correct, Joyce, exactly. That's all that matters. So if let's say, you know, I have ethylene, which is this guy. I have 2 protons to work with, so that means I could use 2 equivalents essentially and use those to play around. Okay. So yeah, if the alkyne is terminal and we want it to be an alkene, does it matter which one we use? No, because there is no easy geometry when it's terminal. But that's a very good question. Because, you know, in order to have easy geometry, you need to have 4 different substituents. And if you're terminal, 2 of those substituents are hydrogens. Okay, so yeah, does not matter. Yep, great. Looks like you guys are getting it. All right, so let's do our last one. So everyone take a second, moment of truth, okay? So everything we talked about should now help you get this one question right, okay? So let's think. I'm not gonna tell you the answer. Somebody think about it. Essentially, I have an alkene and I wanna extend the carbon chain. Boom, something should be going off in my head, which is acetylide, okay? How do I get acetylide addition? Okay, somebody type it in the chat box. What's the first thing I wanna do for this guy? Great, halogenate, boom, BR2, halogenate, great, I love that, awesome. So somebody do that, awesome, BR2, do that on your paper. By somebody, I don't know, I'm just talking to myself. All right, so there we go. You guys are getting it. So you can see the trends. It's really easy for exam 3 at least, because you guys are limited. Okay, boom. Now, again, I need to do acetylide. So step 2, somebody put in the chat box, or everybody put in the chat box, let's see. Perfect, NaNH2, that works. Dehydrohalogenate, if you guys were to say that, that works too. So how many equivalents am I gonna use? Somebody else put that in there. 3, that's great. Why 3? Because there's 3 protons to deal with. This is awesome, you guys are getting it. So I can do, I'm gonna do this all in kind of one thing here. So step 1 is that, and step 2 I would do, you know, it looks like I have a 1, 2, 3 carbon. So 1, 2, 3, looks like 4, 5, 6 and the benzene ring. So it looks like 4, 5, 6 and the benzene ring. So this would be 4, 5, 6 in the benzene ring. Okay, so you guys can see at this point, now we have this structure that looks kind of funky. I'm gonna draw it over here. Okay, so just to verify all these things, remember our starting material had 1, 2, 3 carbons. So that was the 1, 2, 3 carbons. Then we added 4, 5, and 6 in the benzene ring. So that should make sense. Great. Okay. It looks like I'm going to form this syn diol. All right. What are my last 2 steps? You can put them in the chat box. Your last 2 steps. What alkene do I need? And, you know, how do I get those diols on there? Those are the last 2 things. Great. H2 Lindner and then OSO4. You guys got it. So this one had to be that H2 Lindner guy for reasons we talked about. It has to, if it's dealing with the syn diol, it has to be H2 and Lindner. That's going to get me to 1, 2, 3, 4, 5, 6. So 1,